So same chapter, DC circuit. And the topic is potentiometer. Potentiometer is the circuit which measures voltage, potential difference without any voltmeter. So any circuit which is used to measure potential voltage without any voltmeter is called potentiometer. So first theory, suppose this is the battery of EMF E is negligible. It's connected to two copper wires of negligible resistance. The point is B, a high resistance wire is connected between A and B. It's also known as 10-10 wire. We call it just resistance wire, okay? So the resistance of the AB wire is very high. Now suppose with terminal A, a voltmeter is connected, and this is the movable end M. When the M end is placed at A, then the length between A and M terminal is 0. So the resistance between A and M will be 0. So the voltmeter reading for A and M will be 0 because the voltage directly proportional to resistance we have done in the previous topic. When this M contact is moved away from A towards B, then M is moving away from fixed point A, then the length between AM is increasing, resistance between AM increasing. So the voltmeter reading for AM will be increasing. So number one, number two. Now, this movable contact is placed exactly at B. So number three, when M is at length B, so the length between AM is exactly equal to the length between AB, which is the maximum length of the resistance wire. So the resistance of the AM length will be maximum, and the voltmeter will read the maximum value, and that maximum value, V maximum, is exactly equal to EMF of the cell, because the maximum potential provided to the circuit is equal to EMF. Okay, thus the conclusion is when length increases, the resistance increases. When resistance increases, the potential voltage, potential difference also increases. Now, come to the potentiometer circuit. This is the known cell with EMF E with negligible internal resistance. It is connected with two wires of negligible resistance. So this point is X, this point is Y, and the resistance wire is connected between X and Y. Now we have an unknown cell, unknown battery. that unknown cell must be connected parallel to the first, mean the positive side of the unknown cell must be connected with the positive side of the known cell, and no voltmeter. You can add here any galvanometer, ammeter, and then this movable contact M. Now suppose when this M contact, movable contact is placed, is connected at M, the potential between X and M is 0. In this small loop, the unknown cell has some potential. So there will be the potential difference in small loop, and that is unknown because the potential of this cell is not known. Yes, it has potential, and here the potential is 0. So there is a potential difference. So due to the potential difference, current will flow from high potential to low potential, and that current is recorded by ammeter. So when M is at X, the ammeter will show some reading for the current. Now, this M contact is moved away from X. Suppose here now. Now the length between X and M increases. Resistance between X and M increases. So the potential between X and M increases. Now, in the small circuit, this potential unknown, initially the potential was 0. So the difference was maximum. Now here, X and M, this length is not 0. So the potential is not 0. So the potential difference between the unknown cell and XM length definitely will decrease, right? So when the M is at X, the potential difference, this will be maximum. When this M moved away from X, the potential between X and M increases. So the difference between XM and this cell decreases, because suppose one potential is fixed, other potential is increasing, 0, 1, 2, 3, 4. So 15 and 0, the potential difference is 15. 15 and 1, the potential difference is 14. 15 and 2, it is 13. Look, the potential difference gradually decreasing. So when M moved away from X, due to increase in the potential between X and M, the potential difference for the small loop decreases. Hence, the current reading decreases because the potential difference, delta V, is also decreasing when X is moving away from fixed point X. Now, suppose when this movable contact M is placed at this point, say this is Z point, then the potential of the unknown cell becomes equal to the potential of X and Z. Potential of the unknown cell, suppose the potential of this length X and Z, then the potential difference will be 0. So the current reading, ammeter reading will be 0. So when this ammeter reads 0 current, then the point at this wire, the point on the wire, resistance wire, is known as balanced point. Mean This balance point is the point which gives us equal potential both sides for the small loop. So the potential difference 0, current 0. And after finding the balanced point, we will measure the length between x and z. Suppose it is equal to x small. And then we will measure the total length between x and y. Suppose this is the capital L. Now we have done that the voltage directly proportional to R directly proportional to L. So we can write V directly proportional to L, or we can write V1 over V2 is equal to L1 over L2. If V1 is considered the voltage of this unknown cell, and V2 is considered the potential, the EMF of the known cell. So this known cell is giving the potential when the voltmeter is connected between A and B, total length L. So for L length, the voltage is equal to E. And for X length, the voltage is equal to this unknown cell. So we can write here V divided by EMF is equal to X divided by L. Hence, the voltage of the unknown cell is X divided by L into EMF. This is the formula for the potentiometer. For example, this EMF known is 15 volt, and this total length is suppose the 12 centimeter. And this balanced point is coming at suppose 3 centimeter mark. Then the question is, what is the voltage? What is the potential of this cell? So the formula V is equal to X divided by L into EMF. So X is 3, L is 12, and the EMF is 15. So you will get the answer, 3 ones are 3 fours are. So 15 by 4. This is the potential in volt for the unknown cell. Okay, suppose there is a point. If this is the cell of EMF, suppose 9.0 volt, two wires are connected and the resistance is negligible. This is A point, this is B point, and this is the constant and wire being the resistance wire. Now, according to theory, if the voltmeter is connected with A or B, and this movable contact is placed exactly at the mid of the AB, then theoretically, the voltmeter reading must be the half of EMF 9, 4.5. But practically, it will be not 4.5. Reason. Number one is, if the wire is considered of uniform cross-sectional area, and AM has length R, then MB has resistance R. But the problem is, at the junction A, when the current I enters the junction, it divides into two parts, I1 and I2. Definitely due to the high resistance of the voltmeter, this I2 is very, very small as compared to the I1. And then at the junction M, both currents are added, and from M to B, the current becomes I. For example, this current is 5 ampere, 4 ampere passing through AM, and just 1 ampere passing through this. Then from M to B, the definitely current will be 5 ampere. So due to this junction at A, current between AM and MB not same. So according to the formula, V is equal to IR, V is equal to IR, R constant suppose, then V directly proportional to I. So small current, so small potential, and the large current, large potential. So it means both are not equal. This is one of the reason, because resistance same, but the current divides in the AM loop, and M to B current is bigger than the AM, so the voltage is not same. This is one of reason. And second reason is, it is not confirmed when the M is placed exactly at the middle of the AB wire, the diameter of the wire is not uniform. We have no confirmation. Suppose the wire is like this. So this is 0 mark. So this is 10 centimeter mark. This is 5 centimeter mark. So this diameter average is small. This is large. So here resistance is large. Here resistance is small. So when the wire is placed, when the M contact is placed exactly at the middle, theoretically, we will assume that the same voltage both sides, but practically it's not possible due to two reasons. Because number one, current divides at AM and MB have different current. And number two, the wire has no uniform cross-sectional area. Now, same chapter. And the next topic is maximum power theorem. Suppose we have an electric circuit, DC circuit. This cell has internal resistance small r, and internal resistor is always shown in the dotted box along with the cell, because this is not visible. Here is a switch, suppose S, ammeter connected, and here is the external resistor, and this is variable. And then a voltmeter is connected parallel to this variable resistor. This cell suppose has EMF of 6.0 volt. This internal resistance has value 2 ohm, and this variable resistance can be varied from 0 ohm to suppose 10 ohm. Now suppose this S switch is closed, and the external resistance, this capital R, is set at 0 volt. This is 0 volt external. Circuit is switched on. Now, what is the total resistance of the circuit? It will be total resistance 0 of the external, but the 2 of the internal in series. So total resistance becomes 2 ohm. So there will be current, I is equal to V by R. So V is total 6 divided by 2. The current will be 3 ampere. The ammeter will read 3 ampere. Now, what will be the output power across the external resistor? Power across external, I square R. So I is 3, external resistance 0, no output. Current is there, but circuit is giving no output power. Number 2, suppose this external resistor is set at 1 ohm, then the total resistance of the circuit becomes 1, this internal 2, it becomes 3 ohm. So the current becomes V divided by R, so 6 divided by 3, so the current decreases 2 ampere, 3 to 2. So the power across the external resistor, I square R, mean 2 square multiply by resistance 1, so it becomes 4 volts. Look, current decreases and the power increases from 0 to 4. Similarly, number 3, if the external resistor is set at 2 ohm, then the total resistance becomes 2 plus 2 internal 4 ohm. Then the current becomes V divided by R, means 6 divided by 4. I think it's 1.5 ampere. Current further decreases, and the power across the resistor external I square R. So it is 1.5 square multiplied by this 2. So the answer is 4.5 watts. Look, the current is decreasing and the power is increasing. First 0, then 4, then 4.5. Now, number 4, if the external resistance is set at 3 ohm, then the total becomes 3 external, 2 internal, 5 ampere resistance, 5 ohm. Now, current I is equal to V by R, 6 divided by 5. So it becomes 1.2 ampere. Current further decreases 1.5 to 1.2. And the power of the external I square R, it becomes 1.2 square multiplied by 3. So this is 4.32 watts. Now the power starts decreasing. Number 5, if the external resistor is set at 4 ohm, then the total becomes RT. This 4 plus 2, it is 6 ohm, and the current I is equal to V by R. So 6 divided by 6, it becomes 1 ampere. So the power of the resistance is equal to I square R. So 1 square into 4, it becomes 4 watts. Now look at this. Initially, power is 0, then 4, then 4.5, then starts decreasing 4.3, then 4. Look, two values of the power, 4, for different resistances. So this is called the maximum power theorem. So the maximum power is this, which is 4.5. It is maximum when the external resistance is exactly equal to the internal resistance. This concept is called maximum power theorem. Mean the maximum output power from any circuit is possible when the resistance of the external circuit must be equal to the internal resistance of the cell. So when external resistance exactly equal to the internal resistance, then the power out will be maximum. And this concept is called maximum power theorem. For example, we have this external resistance in ohm at the x-axis and the output power in watts at the y-axis. So initially it is increasing and then it is decreasing. And this is the maximum power. Suppose this is P naught, and it is possible only when external resistance equal to internal resistance. Now, power is equal to I square R. Then power divided by R, which is the gradient of the graph, is equal to I square. Look, due to small resistance, current is large. That's why the gradient of the graph is large. And here the resistance is maximum. So the current is minimum. That's why the gradient of the graph is minimum. Okay. And any value of the power lower than maximum, for example, this one, this power is not maximum, smaller than the maximum, can be achieved twice. First at low external resistance and then at high external resistance, like 4 at 2 resistors, 4 ohm and 1 ohm. Reason? Because the power is the product of I square and R. So this is the value when current large, resistance low, current large, because the power is the product of I square and R. So square of the current here is the large, resistance is small, and here when the resistance is large and the current is small, so the product becomes same. So any value of the power smaller than the maximum can be achieved twice at two different resistance. So at small resistance because the current is large, at larger distance because the current is small, and the power is the product of I square and R.